we are diving deep into what has to be one of the most incredible feats of biological engineering.
I know exactly where you're going with this. The heart.
The heart's ability to be its own master.
Mm-hmm.
We're looking at cardiac automaticity, that spontaneous rhythm, and this incredibly complex internal power grid that it has.
It's like an engine that just never stops. And our mission today is to really unpack the sources to understand the cellular secrets behind it.
Right.
I mean, it's not enough to just name the parts. We need to know why. How do these specialized cells just discharge on their own without the brain having to send a signal every single second?
Absolutely. Think of this deep dive as us sort of pulling the blueprints on the heart's electrical system. So for you listening, as we map this out, let's quickly identify the primary architectural points. What are the heavy hitters in this roadmap?
Okay, so we can trace the signal through 5 main structures sequentially. It all kicks off at the primary pacemaker, the sinoatrial node, or, the SA node.
The SA
And
node, okay.
From there, it travels to the atrioventricular node, the AV node. Then it hits this major highway, the bundle of His, which then splits into the left and right bundle branches. And then finally, the signal gets dispersed through the Purkinje fibers, which basically electrify the ventricles.
And what's crucial for you to understand here is that when we talk about this whole electrical system, we're isolating a tiny, dedicated minority of cells.
Mm-hmm.
Our sources really emphasize that these signal generators, these atypical muscle cells, they make up only about 5% of the total cardiomyocytes in the heart.
It's amazing. 95% is for contracting, but this tiny 5% dictates the tempo for all of it.
It's the conductor of the orchestra.
It really is. It's a specialized workforce. And even within that small 5%, we find 3 distinct types of atypical cells. Each one plays a really unique role in either, initiation, speed, or even backup capability.
So let's start at the very top of the hierarchy then, with the literal source of the beat, the primary pacemaker cells.
These are the P cells. And they're the undisputed champions of initiation because they show the highest automaticity.
The highest.
What's visually striking, if you could actually look at them, is that they lack myoglobin. That's the red pigment in regular muscle, which means they look noticeably pale.
Huh. So the pale cells are the ones with the electrical key.
You could say that. They're the quiet, pale powerhouses of the heart.
That's a great visual.
Mhm.
Now, their location has to be key to their dominance, right? Where are these primary pacemakers precisely sitting in the heart's anatomy?
Their location is very strategic. They are concentrated in the SA node, which is right at the junction where the superior vena cava meets the right atrium.
A major crossroads.
A very high traffic point. They also show up in the lower part of the AV node. And that AV node itself, that critical gateway, is located deeper in the right posterior portion of the interatrial septum.
So that placement basically ensures the SA node is positioned perfectly to fire off the charge and spread it across the atria. So P cells start the conversation, they fire that first shot. But once that shot is fired, the signal has to, race down to the ventricles. And it needs incredible velocity to do that job right.
And that's where the second type of cell comes in.
The T cells.
The T cells. If P is for pacemaker, T is often thought of as transduction or, transmission. These cells are built entirely for speed.
So they're the sprinters.
They're the sprinters. Their main jaw is to show the highest rate of conducting velocity. They actually have a pretty low level of automaticity themselves. They aren't meant to start the signal. They're the high-speed relay runners. You find these T cells packed into structures like the His bundle where you need that rapid transit.
It sounds like the system's just incredibly optimized. P cells for power, T cells for speed. So what about the third type? Is it some kind of blend?
It is. They're the versatile utility players. The third type are the Purkinje fibers.
Ah, the Purkinje fibers.
Structurally, they're defined as mixed. They combine characteristics of both P and T cells. So this means they act as a source of both automaticity and extremely high conductivity. They're the distribution network that also carries a latent backup power source.
Ready to step in if something upstream fails.
Exactly.
Okay, now, before the signal even hits that main speed bump at the AV node, it has to get across the atria, the 2 upper chambers. Our sources pointed out something really fascinating here. It's not just a general electrical splash.
No, not at all.
There are specific, dedicated electrical express lanes that connect the SA node to the AV node.
That's right. This dedicated architecture is what ensures the speed and the directionality. These are 3 specialized intermodal bundles that contain those fast-conducting Purkinje-type fibers.
Okay, what are they called?
We have the anterior intermodal tract of Gochman, the middle intermodal tract of Venkbach, and the posterior intermodal tract of Thorell.
So it's not a generalized spread at all. These are 3 dedicated highways, making sure the signal gets from point A, the SA node, to point B, the AV node, as fast as humanly possible.
Or as fast as biologically possible.
Right. It's like a freeway system inside the heart. The signal blasts through those tracks, it hits the AV node, and then everything just slams on the brakes.
And this is the critical moment of timing.
This is the moment.
It's the moment that ensures our heart acts like an efficient 2-stage pump. I mean, if you look at general heart muscle, the standard cardiomyocytes, they conduct at a pretty decent pace.
How fast?
About 1 to 1.5 meters per second. That's fast. The whole pathway is designed to move that impulse from the SA node through the atria and eventually down to the apex of the heart.
But tell us about that bottleneck. Why is there a deliberate and necessary speed bump right there at the AV node?
It's all about filling the tanks. You need the atria to contract fully to push all the blood down into the ventricles before that massive ventricular contraction happens.
Ah, so if the ventricles fired too early, you'd lose all that pumping efficiency.
You would. And this critical pause happens in the upper part of the AV node.
How dramatic is that speed reduction?
It's astounding. Conductivity drops from 1.5 meters per second to this glacial pace of only about 5 to 7 centimeters per second.
Whoa. From meters to centimeters.
That deliberate bottleneck creates a delay of precisely 0.05 seconds. It's a tiny fraction of time, but it lets the atria finish their job before the ventricles get the signal. Without that 0.05 of a second, the system is just chaos.
5 centimeters per second.
Yeah.
That's like going from a race car to watching paint dry. But that pause is the difference between a synchronized pump and a useless twitch.
And once that critical 0.05 second pause is over, the impulse picks up speed again. It spreads through his bundle a bit faster, say 8 to 9 centimeters per second, before it just accelerates rapidly through those Purkinje fibers.
Which ensures the contraction starts at the bottom, at the apex, and squeezes the blood upwards and out. Okay, so we've mapped this system and the timing, but let's go back to the source of the magic here. Automaticity. This property that lets those P cells discharge on their own. What is the fundamental cellular secret behind this?
This is where we get into some really fascinating ion channel dynamics. It really comes down to the cell membrane of the P cells being uniquely leaky. Unlike regular heart muscle cells, which maintain a stable negative resting potential and just wait for a strong stimulus.
Like waiting for a big push to open a heavy door.
Good analogy. The P cells, they simply don't wait. They're constantly slowly inching toward that threshold.
What's causing that?
Well, they are constantly undergoing a slow, spontaneous depolarization. This is caused by some specialized low-threshold calcium channels, yes, but more fundamentally, it's driven by a phenomenon that scientists nicknamed the funny current.
Wait, funny current? That sounds like a joke. Why on earth is it called funny?
It's called funny because it behaves exactly opposite to how traditional voltage-gated channels work. Most channels open when the cell becomes more positive, right? When it depolarizes.
Right.
The funny current channels actually activate when the cell's hyperpolarized, when it's at its most negative, right after a beat.
So it's backwards.
It's backwards. This current is carried by a slow, continuous trickle of sodium ions in and potassium ions out.
Okay, so after the cell fires and resets to its most negative state, these funny channels immediately start leaking positive charge back in. It's like a tiny hole in the bottom of a boat that's always letting a little water in.
That's exactly it. That slow, continuous leak of positive ions causes the membrane potential to just drift upwards spontaneously. Once that drift hits a specific low threshold, the calcium channels fly open, triggering the full action potential.
And that's the heartbeat. No external nerve signal needed. That's what makes the P cell truly self-starting. That distinction, the active leak versus waiting for a big stimulus, that is the key difference that makes the heart autonomous. So how was this hierarchy, this whole gradient of automaticity where the SA node is the boss, how was that actually proven?
The sources outline this really classic physiological experiment. It uses 3 ligatures, basically surgical ties, to physically isolate and test different parts of the heart. And it clearly shows which parts hold the electrical authority.
Okay, let's walk through the 3 steps. Step 1 has to confirm the SA node's dominance.
Right. In step 1, a ligature is tightened around an atrium, and it physically separates the SA node from everything else. The immediate result you'd see on a myogram is just a flat line in the rest of the heart tissue.
A flat line. So the heart doesn't just slow down, it immediately stops contracting.
It stops.
Wow. So that proves that even though other cells, like in the AV node, have that latent automaticity, the SA node's faster rhythm completely suppresses them. It keeps them quiet.
Precisely. It's proof that the SA node is the required conductor for the entire orchestra. So once the primary source is silenced, we can move to step 2, which reveals the backup plan.
The secondary pacemaker taking over.
For step 2, a second ligature is placed lower down between the atria and the ventricle, but this is key, it's loosened a bit to create a partial block to stimulate the tissue below it.
Well, what happens?
The heart begins to contract again. But here's the key observation. The rate is significantly slower than normal, maybe 40 to 60 beats per minute instead of the usual 70 to 80.
So that lower, slower rate confirms that a site further down the line, probably the AV node or his bundle, is woken up and taken over as the new, albeit slower, rhythm generator.
It confirms the backup plan. It proves the hierarchy. The P cells in the AV node have a slower inherent firing rate than the ones in the SA node. That's what lets the SA node dominate. But if it fails, that latent automaticity kicks in for survival.
Incredible. Okay, finally, the third ligature step. This one isolates the receiving end of the signal.
Yes. The third ligature is used to separate the apex, the very bottom tip of the heart, from the rest of the ventricle. When the main electrical signal is allowed to pass down but is physically blocked from reaching that isolated apex,
the apex stops contracting.
It stops contracting.
So even though the ventricle muscle itself can contract, this step proves the signal has to travel down that dedicated electrical highway, the His bundle, the Purkinje fibers, to get to the muscle. It can't just be stimulated by general contact.
It demonstrates the non-negotiable path of the current. This elegant three-part experiment confirms everything. The SA node is the fastest boss, the lower sites are the slower backups, and the electrical impulse has to use the specialized highways to get where it needs to go.
It's truly amazing. What our sources have shown us is that the heart is wired with these specialized cells, P cells, for the internal clock, powered by that funny current, and T cells for speedol, linked by those crucial high-speed tracks like Gachmann, Venkebach, and Thorel. And this creates a spontaneous, rhythmic, and perfectly timed loop with that critical 0.05-second speed bump at the AV node, ensuring we pump blood efficiently.
It just shows the sheer complexity underlying something we take for granted every single second of our lives. It's an electrical system that manages its own maintenance and its own contingency planning, all internally.
And that leads us to a final provocative thought for you to consider. We saw in the experimental evidence that the lower parts of the heart, like the ventricle, can contract if they're isolated, but they do it much more slowly. So what does this intrinsic gradient of automaticity, where every level down the hierarchy has a slower inherent rhythm, what does that imply about the evolution of our cardiovascular system? Is the goal just simple survival, or does that slower backup rate specifically preserve critical energy resources in the event of a primary pacemaker failure? The system is designed not just to keep you alive, but to keep you alive in the most efficient way possible, even when it has to run in emergency mode.